A non-Newtonian fluid is a fluid with properties that differ in any way from those of Newtonian fluids. Most commonly, the viscosity of non-Newtonian fluids is dependent on shear rate or shear rate history. Some non-Newtonian fluids with shear-independent viscosity, however, still exhibit normal stress differences or other non-Newtonian behavior. Many salt solutions and molten polymers are non-Newtonian fluids, as are many commonly found substances such as ketchup, custard, toothpaste, starch suspensions, paint, blood, and shampoo. In a Newtonian fluid, the relation between the shear stress and the shear rate is linear, passing through the origin, the constant of proportionality being the coefficient of viscosity. In a non-Newtonian fluid, the relation between the shear stress and the shear rate is different and can even be time-dependent. Therefore, a constant coefficient of viscosity cannot be defined. Although the concept of viscosity is commonly used in fluid mechanics to characterize the shear properties of a fluid, it can be inadequate to describe non-Newtonian fluids. They are best studied through several other rheological properties that relate stress and strain rate tenses under many different flow conditions, such as oscillatory shear or extensional flow, which are measured using different devices or rheometers. The properties are better studied using tensor-valued constitutive equations, which are common in the field of continuum mechanics. Types of non-Newtonian behavior. Summary: shear thickening fluid. The viscosity of a shear thickening fluid, or dilatant fluid, appears to increase when the shear rate increases. Cornstarch dissolved in water is a common example. When stirred slowly it looks milky. When stirred vigorously it feels like a very viscous liquid. Shear thinning fluid. A familiar example of the opposite, a shear thinning fluid, or pseudo-plastic fluid, is wall paint. The paint should flow readily off the brush when it is being applied to a surface but not drip excessively. Note that all thixotropic fluids are extremely shear thinning, but they are significantly time-dependent, whereas the colloidal, shear thinning, fluids respond instantaneously to changes in shear rate. Thus, to avoid confusion, the latter classification is more clearly termed pseudoplastic. Another example of a shear thinning fluid is blood. This application is highly favored within the body, as it allows the viscosity of blood to decrease with increased shear strain rate. Bingham plastic fluids that have a linear shear stress-shear strain relationship require a finite yield stress before they begin to flow. These fluids are called Bingham plastics. Several examples are clay suspensions, drilling mud, toothpaste, mayonnaise, chocolate, and mustard. The surface of a Bingham plastic can hold peaks when it is still. By contrast, Newtonian fluids have flat featureless surfaces when still. Rheopectic or antithixotropic. There are also fluids whose strain rate is a function of time. Fluids that require a gradually increasing shear stress to maintain a constant strain rate are referred to as rheopectic. An opposite case of this is a fluid that thins out with time and requires a decreasing stress to maintain a constant strain rate. Examples. Many common substances exhibit non-Newtonian flows. These include soap solutions, cosmetics and toothpaste. Food such as butter, cheese, jam, ketchup, mayonnaise, soup, taffy, and yogurt. Natural substances such as magma, lava, gums, and extracts such as vanilla extract. Biological fluids such as blood, saliva, semen, mucus and synovial fluid. Slurries such as cement slurry and paper pulp. Emulsions such as mayonnaise, and some kinds of dispersions. Oobleck. An inexpensive, non-toxic example of a non-Newtonian fluid is a suspension of starch in water, sometimes called oobleck or ooze. Uncooked corn flour has the same properties. The name oobleck is derived from the Dr. Seuss book Bartholomew and the Oobleck. Because of its properties, oobleck is often used in demonstrations that exhibit its unusual behavior. A person may walk on a large tub of oobleck without sinking due to its shear thickening properties, given the individual moves quickly enough to provide enough force with each step to cause the thickening. Also, if oobleck is placed on a large subwoofer driven at a sufficiently high volume, it will thicken and form standing waves in response to low-frequency sound waves from the speaker. Flubber is a non-Newtonian fluid, easily made from polyvinyl alcohol-based glues and borax. It flows under low stresses but breaks under higher stresses and pressures. This combination of fluid-like and solid-like properties makes it a Maxwell fluid. Its behavior can also be described as being viscoplastic or gelatinous. Chilled caramel topping. Another example of this is chilled caramel ice cream topping. The sudden application of force by stabbing the surface with a finger, for example, or rapidly inverting the container holding it, causes the fluid to behave like a solid rather than a liquid. This is the shear thickening property of this non-Newtonian fluid. More gentle treatment, such as slowly inserting a spoon, will leave it in its liquid state. Trying to jerk the spoon back out again, however, will trigger the return of the temporary solid state. Silly putty is a silicone polymer-based suspension which will flow, bounce, or break depending on strain rate. Plant resin is a viscoelastic solid polymer. When left in a container, it will flow slowly as a liquid to conform to the contours of its container. If struck with greater force, however, it will shatter as a solid. Ketchup is a shear thinning fluid. Shear thinning means that the fluid viscosity decreases with increasing shear stress. In other words, fluid motion is initially difficult at slow rates of deformation, but will flow more freely at high rates.